Thanks everyone for leaving the coffee break early, especially early. This is joint work with 3 students. Jacob is here and Denny was supposed to be here. That's why his name is in turquoise also, even though he's not here, but Arjun did just as much work and wasn't supposed to be here, so his name is black. And my students really should be giving the talk. Jacob just announced yesterday that he was coming. He would have given the talk, and good thing we didn't sign up Denny to give the talk because he's not here. Okay. So the worst thing about me giving the talk instead of my students giving the talk is the quality of the slides. So apologies in advance for that. So the topic.
Students make the slides.
Oh, I should have had the students make the slides. Yes. The students were running the experiments up until actually 5 minutes ago. I had an idea during the last talk. Wait, try this. Okay, so what I'm going to talk about today is RLHF. RLHF stands for Reinforcement Learning with Human Feedback. It was mentioned this morning during Kevin's talk. It is a way of aligning the output of a language model with human preferences or human values. It's the kind of preeminent way of doing it. So I claim that this process can be modeled as a game, and probably I'm not the first one to make that claim. And I'm going to present to you a formal model of that game today. And I'm also going to talk about our attempts to solve the game. So everybody here should know that solving games is not an easy thing to do. And so I will show you some of the pitfalls, some of the ways to understand RLHF, and some of the successes that we've had. And as I said, we were running experiments during the last talk, so we haven't quite solved the problem yet. Okay. All right, so a key challenge in AI with the advent of language models, large language models, everybody's very excited about them, but a key challenge is how can we endow these language models with our preferences? How can we get them to, talk sensibly, but talk, in ways that are helpful to us and in agreement with our values? So for example, not to perhaps guide us towards suicide or towards divorcing our spouse, which is, those are some of the examples that we see talked about in the New York Times. So one way to attempt to solve this problem is through what's called reinforcement learning with human feedback. And the idea is that after a language model outputs something in response to a prompt, you have a human evaluate that output. So the human can say, yeah, thumbs up, that sounds like a good output, or thumbs down, nope, that's not very good, let's try again. So that's sort of the human feedback part of it. And the reinforcement learning part of that is that what we want then is from the human feedback to kind of understand the human preferences. So we're going to do some sort of training, some sort of learning from the human feedback to build a model of human preferences. And then the reinforcement learning part is that we're now going to optimize a new objective for our language model, which incorporates that model of human preferences. Okay, so we have a set of outputs from a language model, and we label them with human feedback, thumbs up, thumbs down. And then what we'll do is we'll infer from those thumbs ups and thumbs downs whether we'll infer some kind of reward model, some way of understanding the human preferences, and then we will train our language model again to optimize with respect to those human preferences, or with the reward model that we've just learned. Okay, so that is the idea of RLHF, reinforcement learning from human feedback. And what I just described, here's another slide saying kind of the same thing. Vanilla RLHF, so this kind of 2 steps that I just described, there's actually a step 0. Step 0 was the training of the large language model that we started from. And that step is important because when we get to step 3, which is now we're going to optimize with respect to this reward model that we've just learned, which represents our human preferences, we want to make sure that when we optimize with respect to that reward model, that we don't stray too far from what the large language model had learned in the first place. So we don't stray too far from whatever ChatGPT had in mind. And that's so that we still are speaking coherent English, right? So the human preferences might not have, really articulated that as well. So we want something close to ChatGPT, but tweaked a little bit that will then, align with whatever values we were trying to endow our AI with. So that's the process of vanilla RLHF. So we train a reward model and we then train a language model. So the thing is, as game theorists, we think about this, we train the reward model, then we train the language model. But after we train the language model, you might imagine, well, I have a new language model. How about I go ahead again and I train a reward model? After I do that, so again, what do I mean by that? I take my new language model, the one that I just got out of step 2 here, that was retrained to be not too far from ChatGPT, but incorporate some of my human preferences. And I use that language model now to generate a whole bunch of new examples for the human to then say thumbs up, thumbs down. I learn a new reward model. Based on that new reward model, I learn a new language model, and around and around and around and around. So I'm calling that iterated RLHF. To me, this seems like a very kind of natural cycle, but there's not a lot of that in the literature that I have found. I mean, maybe people will tell me that I'm wrong and that they've seen it and people are doing it. I'd love to know. But I kind of think that, again, it's a natural way to view the problem, I think. But we're not seeing a lot of literature about this approach, possibly because it's a game and solving games is hard. So what we have, and in particular, it's a general sum game. So we have these two different players, the reward model that's trying to, learn the model of the human preferences. And we have the language model that's trying to optimize that reward model. And we can view this as a game between the two of them. And you might think of doing this iterated thing, which is kind of a bit like a simultaneous gradient descent type algorithm. And you would like to see that converge to something useful, potentially, and maybe find the Nash equilibrium of this game. So that's kind of my premise here, my thesis, that this RLHF can be viewed as a general sum game, and that maybe with that perspective, we can try to solve it using some kind of simultaneous gradient descent dynamics that we see used to solve general sum games, and maybe we would see an improvement over standard RLHF by viewing things in this way. So what I'm going to do is I'm going to present RLHF as a game, as a formal game, and then I will show you our attempts to solve the game, which are maybe better than what, I mean, it's hard to say that they're better than what's out there. On the tests that we've done, in some cases, in the cases that we've tested, they are better, but they're very small cases. We're not testing, and we're not using tons of resources and really, testing this at scale. But I have only had moderate success because I think we can even do better, and I'm having trouble doing better than better. So I'll explain that. All right. So we are, what I want to do is I want to present the two players' objectives formally here. So I'm going to define an alignment game, and again, between these two players, the reward model and the language model. So I'm starting with some background, which is that I have some preference environment. So for large language models, what this is going to be is this is going to be a set of contexts. So these are going to be the prompts that you feed to ChatGPT. And then we're going to have some data set. Here I write entities very generically because preference environments can be very generic. We can have preferences between sports teams, or we can have preferences between continuations that come out of a language model. We can have preferences over all sorts of things. So we have a set of contexts. These are our prompts. And now we're going to have a data set, which will be these continuations coming out of the language model. And then we're going to have some preference relation that's going to tell us, yes, I prefer one, or I prefer the other. Okay, so that's the environment that we're starting in. And a typical way to learn human preferences, and this is not the only way, but this is kind of a standard way, and this is what's used in most of RLHF, is a Bradley-Terry model. And so this is just a simple model of understanding that when humans are labeling the continuations that come out of the language model, which they're giving thumbs up and thumbs down, they may or may not make mistakes, right? So sometimes they, I mean, it's easy to kind of think about this in the context of sports teams too, right? So you have two teams going at it. You have the Red Sox and the Yankees playing, and, occasionally the Yankees do win. So like there was a mistake. So, okay, That wasn't funny? Okay. Right, so that's what's going on here as well. And so the Bradley-Terry model in particular is assuming a certain form for the mistakes, and that form is, let's see, does that work? Yeah, okay. So that form is this sigmoidal, and this sigmoidal is looking at what is assuming to be an underlying score. This U function is a utility function, so I have a whole bunch of, so I have my two teams, I have my Yankees and I have my Red Sox, and they each have some kind of underlying score. And so the Bradley-Terry model simply assumes that I'm going to apply this sigmoidal to the difference between some underlying score that's representing somehow the quality of the Yankees versus the Red Sox, or the quality of our two continuations from our language model. Okay, so this is kind of a standard thing, not very important today, except for us to know that when we plug this in, we get a nice shaped, which I'll explain in a second, but we get a nice shaped objective function for our reward model, which is pretty easy to optimize. So that's why Bradley-Terry is kind of the standard choice for representing human preferences, because it's an easy optimization problem. So again, what's the setup here? So we have a context. So, you know, for the sports teams, it's home or away. For the language model, it's whatever you input as a prompt to ChatGPT. We have our two entities, and we have a label, right? One is preferred and one is, let's say, dispreferred. And so the goal is to infer some underlying scores, which I'm calling here U hat. They're parameterized by these omegas. So this is going to be a neural network. So the omega are the neural network parameters. So we want to infer the U hat, and in particular, we're going to try to infer a U hat that's going to maximize the likelihood of our data. So if we have a whole bunch of examples, we're looking at this maximum likelihood objective here. And as I said before, so this is maximizing, right? Remember the sigmoid, that was the maximizing the difference. The sigmoid is applied to the difference between these two scores. So what we want to do here is we want to infer this U hat that were really the omega, the parameters of the U hat that are going to maximize the likelihood of the data. Okay, so that is our reward model's objective. It's a nice objective. It's a log of a sigmoid, and it is concave. So this is actually a fairly, as I said, easy problem, and this is like a well-behaved function that we can optimize. So that's our reward model story. And now we want, okay, so this is the same thing again, but yeah, the same thing again. All right, and now we will have the language model enter this game. Okay, so that's the objective for the reward model. That's the game that the reward model is playing. And what does the language model do? What the language model is doing, as I said, is, you know, given a prompt that's drawn from some distribution, the language model is going to be generating some continuations. So the language model is making decisions about what the continuation should be for that prompt. And so the language model here is parameterized by this theta. So the language model is going to want to optimize this theta. And what I'm showing here is the same reward model as before, but I want to emphasize that the reward model also depends on theta. So how does the reward model depend on theta? There's no actual theta here. The way the reward model depends on theta, theta is kind of in this M. Theta is generating those examples. So we're summing up over all the examples that came from theta. Okay, so the reward model depends on theta here. And now what does the language model want to do? Well, the language model wants to optimize the rewards. Okay, so this is what I said at the beginning. Once we learn the human preferences, we now have this reward model, this R omega, which is representing the human preferences. And now the objective for the language model is to optimize that reward function. Okay, so it's looking for the parameter values, the thetas, for its policy that are going to maximize this expectation, which is we draw prompts from a distribution. We generate continuations according to our policy, and we want to maximize an expectation because there's stochasticity in that policy. Okay, so that is the alignment game. And yes, let's have questions. Who's talking? Yes, yes.
Yeah, so the language model in the first step is giving you two responses.
Sorry, the language model is giving me two responses. Yes, right. Yes.
Feedback you're getting is, when the Bradley-Terry model is comparing like which one is better, you know,
Right.
So I'm confused. We want them to be far apart. I mean, what I don't understand the language models.
So the language model, sorry, say again.
There are two responses.
There are two responses. Okay, so maybe what's missing is the fact that there's this kind of person outside the system who is saying which is better and which is worse. So the language model is not really impacting that part of the problem. So let me try again. So it's too complicated.
Is
That's
it
a big
has to say that the language model wants to generate something that's obviously better than something else? Is that its incentive? Because then
It's not trying to,
there's a lot of
it's
probability to be maximized that way, right? If you get a good.
right, but it's the reward model that wants to maximize that log probability. The reward model is trying to
Oh, I see.
disambiguate those two, right? The reward model is just trying to find some utilities that match those comparisons. The comparisons come from a person. The reward model wants to find some utility function that is going to represent those comparisons. And then the language model is just generating, it has the reward model, which is a utility function at that point. So the language model is not thinking about generating one or generating another. It's just generating, and then they're being evaluated by the human. Maybe, yeah.
So the things that the human's evaluating, are they generated iteratively from this language model or are they from something else?
No, so they're, as the game is going, we get a new language model, we get new generations. We get a new language model, we get new generations. Yeah, that's kind of the point of the iteration, right? So we get to kind of update our reward model.
They're different just because of the stochasticity.
Yes,
models.
yes, that's why they're different. Just their stochasticity in the language model. It's not, they don't have an objective to make them good and bad or whatever. They're
If you
just,
turn the temperature down to 0 and it weren't stochastic anymore, then the game
yeah,
would kind
then
of stop.
there's, yeah, right, there wouldn't be, right, but there's a lot of randomness, yeah.
You just starting with the gamified view being so advantageous here. It sounds like two-player general sum game. And if I do something like direct preference optimization and I just make it directly a supervised learning problem that fits maximum likelihood, what are like the advantages of doing this as?
Well, let's hold off on that and but that's kind of my point. So let's see if maybe there are advantages, maybe there aren't, but let's, yeah. Yeah, I'm viewing it as a game because that's sort of the way my brain works. And then we'll see if I convince you that maybe that's a good thing, good way to look at it. Other questions? Okay, that's my formalism. Yeah, okay, so again, I can't figure this thing out. Right. So again, I have an alignment game now where I have two strategy sets. One is a theta, that's for the language model. One is an omega, that's for the reward model. And I have two objective functions, again, for the language model and the reward model. And I'm in some kind of language model environment, which is where I get the preferences from. And these are my objective functions. Okay, so what are the equilibria of this game? So the first thing I'll look at here is the Nash equilibrium of a game. And what is a Nash equilibrium? In a Nash equilibrium, both players are playing best responses to one another. And so we have here, theta star is a best response to omega star, and likewise omega star, a best response to theta star. So as I said before, iterating on this game to try to learn the equilibria is a natural way that we might approach this. Unfortunately, it's very hard to learn in games. And even when we have nice concave objectives for both players, we're not guaranteed convergence in general sum games. So, and in this case, we do have a nice concave objective for the reward model, as I mentioned, but for the language model, which is optimizing a neural network, we have who knows what kind of landscape that it might be wanting to optimize. So it's not obvious that this is going to behave well, and maybe that's why nobody has written about iterated RLHF. Another thing that you might think about is maybe viewing this as a Stackelberg game. So in a Stackelberg game, you have a leader and you have a follower. And so the follower behaves as they would at a Nash equilibrium, which is that they play a best response to the leader's strategy, but the leader can do anything it wants. The leader is not constrained to play a best response to the follower. So typically, the way you think about Stackelberg, you think about, okay, if I'm the leader, I can like go over here and try this strategy, and now Jacob's the follower, he's my student, right? So he has to best respond to me. And then I go over here and I try this other strategy, and he best responds again. And I go over here, try this other strategy, he best responds again. And finally I decide, well, I'll just stick with this one because that's the best thing for me when Jacob is forced to best respond. So that's the Stackelberg notion and a Stackelberg equilibrium. And so it's also an interesting question how you might learn Stackelberg equilibria in general sum, and in this case, continuous action games. Continuous action because we have neural network parameters that we are optimizing. So I'm taking the game theoretic perspective and I'd like to solve these games. Do I know how to solve these games? Not necessarily. So that's why I asked Yang to come to the talk, because he might know how to solve the games. All right, so here's how we're solving the games. And we are having some success, so I'll tell you about it. So the important thing here is, 5 minutes, okay. So the way that we're solving the games is with a gradient method, so something like a simultaneous gradient descent. And we have our two players and we compute their two gradients. But an important thing that we're doing here is that we're nesting. And in particular, we are nesting the reward model. So like I said, we don't know what the language model's landscape is looking like. It's optimizing some reward model. But we do know what the reward model's landscape looks like. It's nice and concave. So I'm imagining a non-concave setting for the language model, concave for the reward model. So you're sort of somewhere in this landscape. And as you're moving around trying to figure out what the language model should do at any given point, the nesting algorithm is going to let the reward model kind of maybe not run to completion, but like run a lot of steps, like go ahead and let's like really find what the best thing is to do for the reward model at the point where we are for the language model. So that's kind of the point of the nesting story. And the hope is that this might be beneficial in a non-concave game. So this is a non-concave for one player, concave for the other player. And actually what we're finding, all right, I'm going to skip some things, we regularize, and that's how you compute gradients. Oh, well, that's maybe slightly important. To compute the gradient, we use the policy gradient theorem. So reinforcement learning, you can look that up in the textbook. But so the algorithm that we're running here for this nest, for trying to compute at this point a Nash equilibrium, and using this nesting is actually doing something useful. And here's some experiments where we experiment against DPO. And we're showing that we're outperforming DPO in these experiments. So we have 4 experiments, sentiment generation, word collection, unique nouns, a bunch of things. And the results look like this, which come from the DPO paper. DPO stands for direct preference optimization, kind of a foundational paper in this space. And so we're using the same kind of metrics that they're using here. And what are they? That we're plotting a Pareto frontier, which is comparing a KL divergence and a reward. So the KL divergence is how far you deviate from the original language model, from the ChatGPT or whatever you started with, because remember, we still want to be pretty close to, some coherent English. And then the reward is obviously, how high is your reward? So to do well here, oh, this thing crashed. To do well here, you want to be, high up around. And our stuff is the red. So nested RLHF is red. And, on that Pareto front, it's looking pretty good. And the graph on the right is showing the mean rewards. So what I'm trying to show here is that the nesting idea is kind of working here. And I got that idea from trying to solve a game. So I kind of think the game theoretic perspective is helpful. And we have a bunch more examples. The one that looks like it might be competing with us in the first experiment is the purple. The purple is a backward story where we nest instead the language model instead of the reward model, and it's not very sensible. So it somehow did well here, but it starts to really cause chaos in our other experiments. So I wouldn't go that route. So the claim is that the nesting idea, which I got from game theory, is working pretty well. So the thing that's not working for it, oh yes, Yank.
So for DPO, do you just run one round, or you also do this iterative?
Well, for DPO, you don't really need the iterative thing. Like DPO is kind of.
Yeah, so for DPO, all the preferences are kind of collected on the reference policy.
It's kind of it's almost, I think.
But like if you sample again, you can still do your thing to retrain the reward model or.
Yeah, I guess you could do iterative DPO where you keep sampling, you do some steps of DPO, you sample new
We
completions.
didn't do that. We
we
didn't do that.
should
We can do
Maybe
that.
do that,
We'll
yeah.
let you know tomorrow, okay? Good question, thank you. Thank you. That's why we're workshopping the ideas here. So the other idea we're workshopping is the Stackelberg idea. Oops, we're not workshopping it here. Okay, so the other idea we're workshopping is whether we can actually do better with Stackelberg. And so what's the difference between Nash and Stackelberg? I showed you the definitions of the equilibrium, but actually to compute the gradients, the Nash gradient is kind of this relatively simple thing from the policy gradient theorem, but the Stackelberg gradient is it's a more complicated mess, which is why we're having more trouble. Inverse, Hessian, vector product, something. So that's that formula there at the bottom. So, but it's kind of sensible also, like what's going on there is that we're acknowledging that when the language model makes a change in its policy, there is going to be an ensuing change for the reward model. The reward model is now going to have to optimize. So we can't sort of just like assume that we're holding the reward model fixed and just optimizing, taking a gradient with respect to the language model. We're acknowledging that when we take that gradient for the language model, we see a change in the reward model. And that's why we get that big, messy, complicated gradient. But there's reason to believe that that could do even better than what we're seeing for the Nash gradients on the nested algorithm. So that's the direction that we are going at this moment. Yes?
Quick question, what is W star in this Nash?
What is W star? Right, W star is from my definition of Stackelberg, which maybe is on a, yes, W star is this W star here, which is, remember that Jacob had to best respond to me every time I fixed my policy. That's what W star is. So we're saying, we're acknowledging that W star is a function of my policy. Like what Jacob does depends on what I do, and we're paying attention to that, but that's only in one direction. That's not true in the other direction. I don't pay attention, Jacob can fix his policy, but I'm not bothering to best respond to that. Okay. All right, great. So I think I'm out of time. So let's just I'm going the wrong way again. Okay, the takeaways are, I think the game theoretic perspective is a helpful one to take. I think also that this is a non-concave game, and non-concave games are unsolved and difficult to solve, and maybe, according to Kostas Daskalakis, a challenge for the next 100 years. Maybe we can make some progress like in the next 10 years, but okay, might take us 100 to solve them. But a very important area of research, and something that would also potentially inform the development of foundation models. And for our work in progress, what's still going on is we are looking, as I said, at an iterative version of RLHF with the Stackelberg gradients, those more complicated gradients. There's no reason to be wedded to Bradley-Terry. We can look at other preference models. And of course, as Kostas said, we can work to develop a theory of non-concave games. Thank you.